Good afternoon, everybody. So today we will be entering chapter 5, which is on electromagnetic induction. So there are 5 subtopics, I think, in this chapter, and the first subtopic is on magnetic flux. Okay, so in this subtopic, you should be able to define and use magnetic flux and as well as use magnetic flux linkage. Okay, so what is magnetic flux? Magnetic flux is a phenomenon of an electromagnetic induction. Okay, so Michael Faraday, he conducted some of the experiments that led to the discovery of Faraday's law. If you still remember what is Faraday's law, so the first experiment that he did is he showed that when a ball magnet is stationary, when a ball magnet is not moving, the galvanometer, which is this one, does not show any deflection. So when it does not show any deflection, it means that there is no current flows in the coil. Okay, and the second experiment that he did is by moving the magnet towards the coil here. Okay, so the effect of that movement causes the galvanometer to show a momentary deflection to the right. So when there's a deflection on the galvanometer, it is showing us there is a current flowing through the circuit. Okay, so the third experiment that he did is not the third experiment. This is, should I say, I think we can say that. Okay, so and then after that he tried moving it away from the coil. Okay, so by moving the ball magnet away from the coil, it causes the galvanometer to deflect in the opposite direction. Okay, so before it was on the right and now it is on the left. It is basically showing us the direction of the current lah, begitu. Okay, so therefore, when there is any motion between the coil and the ball magnet, the current that is flowing through the circuit is known as an induced current. Okay, so induced current will flow momentarily jalah through the galvanometer. Okay, so why does the current how did the current being produced is due to an induced EMF lah, ada induced EMF across the coil. Okay, so in conclusion, when a magnetic field lines through a coil changes, the induced EMF will exist across the coil. Okay, right, so the magnitude of this induced EMF depends on the speed of the relative motion, where if the speed increases, the induced EMF increases, and vice versa, meaning that the velocity is directly proportional to the induced EMF. Okay, now magnetic flux of a uniform magnetic field pula. Okay, so this one for a uniform magnetic field defined as the scalar product between magnetic flux density with the vector of the area. With the vector of the area meaning there is an angle between them two lah. So the theta here is showing us is the angle between the magnetic flux density and the area lah. Okay, so it is a scalar quantity and the unit is Weber ataupun Tesla per Tesla meter squared. And yeah, okay, so let's consider a uniform magnetic field passing through the surface, for example shown here lah. Okay, so if you look at this, the area, kalau kamu ada surface macam ni, the area is always perpendicular to the surface lah. Okay, so area punya vector always perpendicular to the surface of the surface lah. Okay, so the angle here, as you can see, the angle between this area and magnetic flux is 0 degree, hence it will gives us a maximum magnetic flux density. Okay, magnetic flux. Okay, so when theta is equal to 0 degree, magnetic flux is at a maximum lah. Okay, terbalik dengan yang last chapter, it was sine theta instead of cos theta. Okay, so an angle of 0 gives us a maximum magnetic flux. Okay, so the other one, it is showing us where the vector area is 90 degree to the magnetic flux. Okay, so because of the vector area is perpendicular to the magnetic flux density, that would gives us the magnetic flux value to be equal to 0 lah. Maksudnya this is a minimum and this is a maximum lah. Okay, so the direction of vector A is always perpendicular to the surface area, and then the magnetic flux is proportional to the number of field line passing through the area lah. Okay, all right. So yeah, that is on our first subtopic, which is on magnetic flux. So magnetic flux is V lah. Okay.